Okay, so good afternoon, everybody. I've been tasked to talk about cosmology from EM observations. So I'll get into it straight away. So there are different kinds of cosmological probes that we know about, and especially from the electromagnetic side, you can think about probes which look at the geometric relations in the universe. So these geometric relations involve things like distances, different kinds of distances to electromagnetic objects, and their redshifts. So you want to probe the distance redshift relations. Okay? So one of the favorite things that people know about is the cosmic microwave background. So you can measure the angular diameter distance, for example, to the last scattering surface using the cosmic microwave background. Then there are type 1a supernovae, which you can use to get the luminosity distance measurements to galaxies in which they blow off, right? And you can get the spectroscopic observations of these galaxies to then determine the luminosity distance and the redshift relation. Then there are things called baryon acoustic oscillations. So these utilize the size of the sound horizon as a standard ruler. And then you can take this standard ruler, try to locate this standard ruler in the galaxy distribution. So you want to figure out whether you can measure the angular size of this standard ruler by using galaxies and the clustering of galaxies. So that's the baryon acoustic oscillations. So this gives you the angular diameter distance to the redshifts of those galaxies. Then in addition to that, you can also use something called gravitational lenses. So these are objects like these, for example, where you see multiple images of the same quasar coming from behind. And because they are taking different paths through space-time, they take a different time to come over to us. And so if the source is flickering, then you see that each of these images, they arrive at you at different times. And so you can use these time delays between the different images to also learn about the angular diameter distance ratios in particular between the lens in galaxy. So for example, the yellow blob here and us, and the source, which is these quasars here that you're seeing, okay, and us. So these are the geometric probes. And famously, using most of these geometric probes, in particular the type 1a supernovae, people have figured out that the universe at late times have been undergoing an accelerated expansion, right? Which has led people to understand this by using something like dark energy or a cosmological constant, right? So the same kind of things you can actually also explain. So all these geometric probes, for example, you can explain them if you just modify your theory of gravity as well, right? But when you do that, then you typically also modify the growth of structure and how structure is growing as a function of time in the universe. Okay? So in order to probe this, so that you're complementary to the geometric probes, you can look at also growth of structure probes. And in these, the first of the things that came up was, for example, the abundance of galaxy clusters. So you can look at galaxy clusters and how they are growing as a function of time, not just in mass, but also in numbers at fixed mass cuts. And then they can help you to figure out how the structure is growing in the universe. So then you can also look at the evolution of the clustering of galaxies and its galaxy-galaxy lensing signal. So that allows you another probe. You can also look at redshift space distortions, which is the large-scale correlations between velocity flows onto large overdensities as probed by galaxies. So they also contribute to growth of structure measurements. And lastly, what you can also do using something called weak gravitational lensing is to map out the entire dark matter distribution. And once you map out the dark matter distribution, then you can study it in chunks as a function of redshift. You try to reconstruct you try to do a tomographic reconstruction of the dark matter distribution, and that again allows you a measurement of the growth of structure. So there are a variety of cosmological probes that have come into the picture, and fortunately or unfortunately, a simple 6-parameter cosmological model with something like dark matter and dark energy being the dominant components, this still remains a good description of a wide swath of data. And there have been some mysteries that have emerged, but this seems to be the model that we have converged on, right? So let's just focus on the mysteries for the moment so that we can make some progress. Maybe we can learn a little bit more about these components from there. So in terms of the mysteries, I would like to list 3 of them in particular. So the first one is, for example, the amplitude of density fluctuation. So I told you that we have these growth of structure probes, right? And so you can look at these growth of structure probes and you can ask what measurements of Planck tell you about what this growth of structure should look like. And you can measure these growth of structures at low redshifts. And you can ask, is the amplitude of density fluctuations that you see at late times, as predicted by Planck, does it agree with the observations that you see by using large-scale structure probes? And it seems there is a slight tension or discrepancy there. There's evidence of maybe a 2 sigma kind of hint, but most of the surveys doing things like weak lensing or redshift space distortions, all of them seem to point towards a slightly lower amplitude of density fluctuations than predicted by Planck. Okay? So that's the first mystery. The second mystery is related to distance measurements at high redshifts from baryon acoustic oscillations in the Lyman alpha forest. Now, this particular discrepancy is also something which is hard to explain. Most people in the field say that this has to be some sort of systematics that they have still not figured out. And so that is another mystery that has emerged. And the last mystery is something that Achisman also talked about, is the Hubble constant, right? So if you take the Hubble constant from something like the Planck cosmic microwave background analysis, and then you compare it to the measurement of the Hubble constant from local probes, then it seems that there is a slight difference between the two, right? And what exactly this difference is and so on, that's again active research work, right? So I will focus on the last one, just because a lot of interest is there in the gravitational wave community about trying to measure the Hubble constant as well. So let's focus on this. So here's a plot from Rees et al. 2016. The y-axis doesn't mean much. The x-axis shows you the Hubble constant measurement. Okay? So the measurement from Rees et al. Is here. Okay? So this is about 73, 74. And then you are seeing different kinds of measurements. So these are mostly local probes. And then these measurements here are the cosmic microwave background results. Yeah.
So we fit on that plot now.
Yeah, that's right. Yeah. So this is from 2016. So there's new data which allows you to get on this plot using gravitational waves. That's right. And so what you have to look at is, this is the latest CMB result. So this is from Planck. And then these are the measurements from Rees et al. And you see that there is a difference between the two. And the question is this difference real or not? If it is real, then in principle, we could be witnessing a breakdown of the 6-parameter lambda CDM model, right? So how can we break it down? So for example, if the equation of state for dark energy, W is not equal to -1, but you change it a little bit, or you allow it to change it a little bit, these measurements from Planck can move over to this side, right? You can change the evolution of the equation of state of dark energy. You can add in extra number of degrees of relativistic freedom, and that can also move things over here. You can allow for curvature, and that also moves things a little bit here. So in principle, we could be witnessing a breakdown of the simple 6-parameter model, right? And that would be exciting. But then all these things, all these comparisons, they do require precise and accurate measurements of the local H0, right? So that's what we need to do. So Adam has been spending a lot of time trying to do this, and it's really a tall task, okay? So it's not at all easy. Most of the times people say that these come from supernovae measurements, but it's much more than supernovae that goes into these measurements, okay? So what you're seeing here is the distance ladder which you need to build up. If you just take the supernovae measurements, then you cannot get the value of the Hubble constant. And the easiest reason for this is, if you want to know that, then you need to know the absolute magnitude of these type 1a supernovae, which is uncertain, right? And so to calibrate the absolute magnitude of type 1a supernovae, you need extra electromagnetic observations in more nearby galaxies. So how is this done? So to do that, you start off in this particular plot, okay? So this is C-feeds, okay? And you have observed magnitude for them and some absolute magnitude for them that you don't know, okay? Again, for the C-feeds, you don't know what their absolute magnitude is. And so what you have to do is you have to calibrate them with some geometric measurements of distances. Okay, so you look at objects or galaxies which have the C feats, and you should have those same galaxies. You need to have geometric measurements for them. Okay, so the way to do that in the Milky Way is, for example, to look at parallaxes. In the LMC, there's things called detached eclipsing binaries that you can use in M31 as well. But then the most precise measurement that has been obtained so far is from NGC 4258, okay? And there are measurements of masers in this particular system. And so you can look at these masers going around the black hole, okay? And you can measure their velocities, their precise positions using VLBI observations. And you can also measure the change of positions and the change of velocities. So that allows you to then get geometric distance measurements to this galaxy, okay? So that allows you to put, to get an absolute magnitude, which will put the distance measurements here and the distance measurements here on a 1:1 line. So then you take these geometric relations from Cepheids, then you move over to galaxies which have both Cepheids and type 1a supernovae. Once you do that, then you get the absolute magnitude of type 1a supernovae, and then you move over to the supernovae Hubble relations to calculate what the Hubble constant is, right? So it's a very tall task, and this is what you need to go through in order to do this. So of course, you can expect improvements from Gaia parallaxes that can happen that will help you to tie and pin the Hubble constant down even further. The other thing you can do, as I told you, was by using gravitational lensing, right? So you can measure the time delays of each of these systems, but then there are lots of degeneracies as well in terms of what is the lensing model for this particular galaxy, okay? And to do that, what you need to do is to look at Hubble Space Telescope measurements and try to model each and every pixel within this image in order to get an idea of what the lensing model for this galaxy would be, okay? So that allows you then to break these degeneracies and measure the Hubble constant. So you can expect progress in this by finding many more such gravitational lenses by wide field imaging surveys. And there are a number of such surveys going on right now. Okay, so how do gravitational waves help? As Archusman told you, if you have a binary neutron star merger, a single event can give you a lot of information about the Hubble constant. There is a degeneracy with the inclination, as he mentioned. And if you can use, again, these VLBI measurements of the jet that help you to improve upon the Hubble constant measurement if you just use the gravitational wave data alone. Right? So then this is something that you can do if you have these binary neutron star mergers, and if you can locate and localize what the galaxy is in which this merger happened. But then there are many more and numerous CBC events, right? So where there are binary black holes which are merging. And so we need to be able to also be able to use these kind of events as well, right? So one of the ways, as far as we know, we don't have any of these black EM counterparts for these, but we cannot rule them out completely either, right? So there are surveys like the Large Synoptic Survey Telescope, which are going to go deep. You know, as soon as you give us a trigger, we are going to drill deep into that particular region in order to try to find whether we can get a counterpart, right? Nature can throw curveballs at us, and we should be ready for that, right? So this is the way that LSST is going to operate. I think a fraction of the time is going to be devoted from the main survey from LSST in order to look at these kind of events as well. This is, of course, a high-risk, high-reward project, but in principle, you can do more, right? So as Archusman mentioned, you can try to use the galaxy catalogs which are nearby. So one of the things that Archusman mentioned is that you have to worry about incompleteness in these galaxy catalogs. And this kind of problem actually also happens a lot of times in weak gravitational lensing. We try to measure the distortions of galaxies as a function of their photometric redshift distances. And we need to know whether these galaxies are at the same redshifts or not, as implied by their photometric redshifts. And so in order to do that, what we do is a cross-correlation between galaxies and these binary black hole mergers. Okay, so and the weak lensing galaxies. So you can do the same kind of thing with binary black holes as well, and hopefully that can help you to get the Hubble constant with a great accuracy. So we are also working on these kind of projects. So Anthony, there is a postdoc at IUCAA who is working with me and Sukant on these kind of topics. Okay, so I would like to end here. Just the last thing that I want to mention, we should be ready for new things as well. So there are things like maybe gravitationally lensed gravitational wave events that we should be looking out for, right? These are not necessarily searched right now, but those would be interesting as well. We can also try to figure out whether we can learn about the nature of dark matter and primordial black holes by using these kind of events. So we can defer this discussion to the discussion session. Thank you.